So we now talk about sum and product over points of a PPB. APP. So let us see first sum of function values. So let f be a function from Rd to R. So it takes one location and gives one value. So every location will have some value. And if I want to compute the sum of this function over all points, what I am going to do is I'll take this point process phi. I go to each point, compute the value of this function, and then add it. So sigma xi or fxi, that is my sum, and it will be a function of phi. So if I change phi, this function, this number set of points will change, each function value will change, the sum will change. So this is a function of phi, and because phi itself is a function from omega, so this itself is a function of omega, and so this is a random variable. Okay, so this sum is a random variable because every time you do a different realization, you get a different value. So if this is a random variable, you can define its distribution. You can also define an expected value. So in this part, we are interested in the mean value of S. So the mean value of S is defined as expectation of summation of fxi. So let us see how do we compute this. We will take this example that a point process take two realization, phi1 and phi2. Phi1 has 2 points, phi2 has 3 points. And my function here I'm taking is mod of x square. Okay, so or absolute value of x is norm of x square. So for this realization, if you take this realization, the value of s would be, I have 2 points. So for this point, the function value is 0 square plus 1 square 1. And for this one is also 1. So for this, the addition would be 2. So S takes value 2 if this is the realization. And what is the probability of that? It is 1 by 4. So S takes value 2 with probability 1 by 4. Similarly, if this is the realization, the value is 0 plus 0 square 0, 1 plus 1 square 2, and 2 plus 2 square is 4. Sorry, 4 plus 4 is 8. So the value here would be 10. And this happens with 3 by 4 probability. So the point process takes, the S takes value 2 with 1 by 4 probability and 10 with 3 by 4 probability. So the expected value would be probability plus value, probability into value, this value plus probability of this into value of this. So you get 1 by 4 into 2 plus 3 by 4 into 10 and you get 8. Okay, this is a discrete case, means the realizations are only 2. If you have more realization, a countable number of realization, you can add over all those realization. Or if this is uncountable number of realization, then you have to integrate over the distribution. So to compute that, I'll talk about this notation which can be helpful. Some cases you can directly calculate this, but for more complicated point processes, you may need a different notation. So we have talked about this particular notation that if I have to sum over indicators over phi, which means that suppose take this total number of points in a set A is, you go to each point of phi and ask, are you in A? And whoever says 1, add them all. So in this case, this is my set A. I go to each point and I will ask to all of them, and only these number of points will say yes. So this will be total number of points. Instead of that, what I can also do is I can divide this complete space into small subsets. For each subset, I find out how many points are there, and I only add these functions over the subset A. Okay, so all the A sub intervals in A, I will add their number of points. Like this has 1 point, this has 2 point, like this. So phi dx is the number of point in this small set, which is 0. Phi dx in this set is 1. If I add over all those intervals, I also get total number of points in A. So these two are same. Here it's a summation because they are fixed counter number of points. Here this is the integration because these intervals are uncountable. So this indicator can also be extended to functions. So here only I have xi. What if I have function x here? So let us see this summation. Function multiplied by indicator xi belongs to A, and I'm adding over all phi. So you go to each function points in phi, find out its value xi, fxi, and the indicator that xi belongs to A. Like if you don't have this, then I am adding over all points. If you have this, then you are adding only on the points which are in A. Okay. You can treat the whole thing also as a function gxi. So this means I go to only this set A, and I will take all those points, compute their functions, and add them. Instead of that, I can also divide the complete small space. I go to this only this set, and for every interval, I found out how many points are there. That will give me phi dx. And because this is a small set, the function value at any of the points in this set should be same and should be equal to fx. Okay, so if you take this interval, or suppose this interval around x, there are 2 points. So phi dx will be 2. And the value at both points will be equal to fx because this is a small interval. So the variation would be small. So I'll just take fx, multiply by 2 because phi dx, total number of points, and integrate them over the space RD. Okay, or integrate, if you don't have this indicator, want this indicator, you can just integrate it over set A. And you will get the same thing. So go to each interval, find out how many points are there, multiplied by their values, and then add these values, you get the same thing. And if you don't have this indicator, then this summation will be over all complete space, and here would also be over the all complete space. That doesn't change anything. So what our goal here is to represent that summation of this function fxi should be fxi, indicator xi belongs to A, xi which summation over all points of phi. This can also be written as the following format, that you can divide the space into intervals. You take each interval, find out how many points are there, that will be phi dx, multiply by the function value at the center, okay, and integrate them over the complete space. Okay, just notice that here there is summation because there is a countable number of points. Here there is an integration because there are uncountable number of intervals or subsets. So this notation, why are we interested in this? This notation can help us computing the average value. Because if you compute the expectation here, what you have to do is you have to go to, for every realization, find out probability, compute its value, and then average it over. This can give you a little bit easier notation. Let us see how. So let's take expectation on both sides. This will be just expectation of S, or expectation of summation over all function values of points in A. And then if I denote this way, I'll get this expectation. Now if you look at this, because expectation is a linear operator, it can go inside the integration. And then further fx and indicator are deterministic. So they can be pulled outside the expectation, and expectation will only be here on this term. So it will be integration of fx, indicator x belongs to A, of E of phi dx. Now if you look at this, expectation of phi dx is the average number of points in the set dx. Okay, so what is the average number of point of in a set dx is capital lambda dx by definition. Okay, so capital lambda of A is the number of points in that set A. So capital lambda of dx is the total mean number of points in the interval dx. So what I get is a deterministic integration fx into lambda dx over set A. Okay, so this is a very simple result. If I have to compute this, I will just take function, compute the expectation measure, integrate it over that. And if lambda is has a density, that lambda dx would be equal to lambda x into dx. If it's a uniform, then this will be equal to just lambda into dx. So this is known as Campbell theorem. It says that for a general point process with expectation measure capital lambda and some function from Rd to R plus, the following is true, that expectation of this summation is equal to fx into lambda dx. And if this lambda dx has a density, then it is equal to lambda x dx. And if it's a uniform, then lambda x would be just lambda, which can be pulled outside. And this result is especially helpful in computing the mean of a random variable, which is of the following format, that it goes to each point of the point process, compute the function value, and sum it over all those points. Let us see an example of Campbell theorem. We want to show that Campbell theorem holds for a binomial point process with one point in set W. So this binomial point process has only one point and it is in the set W. So the only point it has, let's call it x1. So the function is f. So the s is f equal to x1 and we want the expected value of this x. There is no summation because there is only one point. So to calculate this, suppose we don't want to use Campbell theorem, we will do an alternate way and show that it will be exactly equal to what Campbell theorem will give us. So expectation measure of binomial point process is lambda a, and lambda a should be such that if I put here w, lambda w, that should be 1, because mean number of points in w should be 1 because there is only one point. So the probability for a point to be set in set A is lambda a by lambda w. Okay, this is from the definition of the binomial point process, that for each point, and there is only one point, the probability to be set in is lambda a by lambda w. And because lambda w is 1, it will be just equal to lambda a. So how do we compute the expectation of S? Note that first we divide W into many intervals, or each is dx centered around x. And now there is only one point, so that point can only be in one of these sets. So if it is in, suppose, a particular set dx, probability for the point to be in that set dx is lambda dx, and then x value would be fx. So, and there are many such sets, and S can only take one of these values. So the expectation would be, if I add over all these intervals, fx into lambda dx, and then integration because it's a continuous summation. So this is exactly what Campbell theorem will give us also. Now, we also want to show that Campbell theorem holds for BPP with n points in set W. So in that case, let's call Si equal to fxi, that is for one xi point. And then the total summation would be summation over all those si's, sigma I fxi's. Okay, here there is a typo, it is fxi. So expectation measure of binomial point process in this case is also lambda a, but note that lambda w is actually equal to n because there are n points. So the probability for the point to be set A is lambda a by lambda w, so it is lambda a by n. So now we do the same thing, we divide w into many intervals dx. One point can only be in one set. Let's focus on one point xi. So probability for that point to be in set x is lambda dx by n, and si's value would be fx. Okay, sorry, not si's for that particular si value would be fx. So the expectation for that case ESI would be integration of fx into probability, which is 1 upon n lambda dx, and then integration over the complete space or intervals. Now note that for because S is a summation over effect size and ESI is this one. So ES is summation over ESIs. And note that this is independent of I. So every point has the same value. Okay, this is intuitive because every point in a binomial punt process is independent and identically distributed. So ES is equal to this one. And because each of them are same, this is just equal to n into ESI. And ESI value, I put it here. This n and n cancel, and what you get is fx lambda dx. This is again equal to the Campbell theorem. So we just showed that Campbell theorem holds for these two processes, and I could have directly computed this one. Let us see one example of Campbell theorem where it can be applied. So we take an example where you have a homogeneous Poisson point process. So it's a uniform point process with density lambda. I assume a power law path loss and a constant transmit power. So in that case, if you want to calculate the mean interference at the origin from the base stations, so these base stations are distributed as a homogeneous Poisson point process. So I am only interested in base station located in this ring. This ring is from A to B. So inner radius is A, outer radius is B, and I want to compute the interference coming from these base stations. So what will be the total interference from each base station? The interference would be transmit power divided by xi to power alpha. This is the path loss. And then I am multiplying the indicator that xi norm should be between A to B so that I am only calculating for the ring. And this is from one base station. And if I add it over all base stations in phi, I get the total interference. Now, if someone wants to ask what is the mean interference, we can compute. So here interference is again in the form of summation over all points of some function of xi. This is a function of xi. So this is the region we can apply Campbell theorem here to compute the mean of interference. So E of Ii is given as expectation of this. You can treat it this as a function of xi, so it will become lambda into integration of fx dx. Fx would be p upon norm of x to power alpha, indicator of A from x to B. Now this is an indicator from A, so I will convert it to a polar coordinate first. So once you convert the polar coordinate, norm x become r. This indicator becomes A from r to B, and dx becomes r dr d theta. And then you have a two-dimensional integration. This is independent of theta, so this will be just 2 pi lambda. And then you have p to power alpha r dr, and this indicator will integration from 0 to infinity, but you have r can only be between A to B, otherwise this will be 0. So this is eventually integration from A to B. So I can compute this further, and what I get is this expression. So what we can see that we can compute the mean interference using Campbell theorem because interference is in the form of summation of the function. So that just tells how important is Campbell theorem and where it can be applied. Now we will discuss some of the functionals for point process. So first is probability generating functional. Let there be a function f from Rd to R. So it takes a location and gives a real number. And let's assume this is a positive number. Then probability generating function is defined as you go to each point and then you compute the value at that point, and then you multiply this value at every point, and then you compute the expectation of it. That is known as the probability generating function. Note that it is functional because it is a function of functions. If you change function, you will get a very different value. Now if I know the value, this value for every function, it uniquely characterizes the point process. So 2 point processes, if they have same BGFL, it means they are same in distribution. So let us see how we can compute this. for a, let's assume there is a function. The PGFL of point process phi is given as this. And if we take an example, the standard example we took, there one point take two realization. One is this one and this one. So for PGFL, if want to compute for the first realization, what is the value of function? At here it is 1, it is also 1, so the product is 1. This means this product takes value 1 with 1 by 4 probability. Similarly here, this is 0, this is 2 and this is 8, so product is 0. So this takes value 0 with 3 by 4 probability. So expected value would be 1 by 4. Let us compute the PGFL of uniform binomial point process in one point in domain W. So the PGFL is defined in the following format, and you have to take a product over all points, compute fxi, and then take expectation. Now there is only one point, so there will not be any product, it's just one function fxi. So let's call it fx1. So what I am interested in computing the expectation of fx1. Now this we have already computed in the past. E of fx1 is given as integration of fx lambda dx. So if I put that will be my PGFL. Now let us extend this to compute the PGFL of binomial point process with n points in domain W. So the PGFL is again given by this, and there are fixed n points here. So this is a product over n points for each fxi. Because this is a deterministic product, I can take this product outside the expectation, and this will become the product over n terms of E fxi. Now note that each of these terms is same. Okay, these are points are identical, distributed. So E fxi and the sum product of similar n terms would be just this term multiplied by n times. So this will be this to the power n. So what I get is expectation of fxi to the power n. And this I have already computed in the past. This is given by this way. So if I take and replace this, I will get this PGFL expression for the binomial point process. We now compute the PGFL for PPP. We first tell the result that for a PPP with density lambda x, the PGFL is given as exponential 1 minus of x lambda x dx integration over RD. So now we'll see its proof. We'll start with the uniform Poisson point process, and first we will only take points inside W. So I'm going to define a new function x gx, which is fx if x is in W, and otherwise it is 1. So all the other points which are outside this set W, their value is just 1. So if you multiply them, it will not change the product. In other words, I'm only considering the point inside W, and for outside point I'm just ignoring them. And if this W is large enough, the PGFL at G would be equal to PGFL at F, because eventually if you take W very large, you end up taking all the points. So let us compute the PGFL of G first. So to compute that, I am going to condition that W has n points. This W is finite set, so it will only take finite values, and the number of points in W is a Poisson distributed random variable. So first condition that it has n points, and once I condition that, we know that the whole point process looks like a binomial point process in W, which means each point is uniformly distributed in W. So what will be the condition PGFL conditioned on that their endpoints is going to be equal to this. So this is because they are endpoints, and for each point the expectation of gx would be expectation of gx dx 1 upon a size of W. So dx upon size of W is the probability that the point will be in x. You multiplied by gx and you integrated over set W, and because each point is identical, the expectation of product of n points would be equal to this to the power multiplied by n times. So this power to the power n. Now, for unconditional PGFL, now I have to take this distribution of n and decondition it. So the PGFL unconditional PGFL would be, you take summation over all values of I, you compute probability that this n is I, and then you multiply the PGFL condition that this is n equal to I, condition on n equal to I. So probability that n equal to I is equal to this value. This is because n is a Poisson random variable with parameter lambda into w, and then this conditional PGFL is given here like this. So what I have is this, and first I notice that this is in the form of 1 upon I factorial into some constant to power I, and we can this is same as this one, that is summation over x to power I divided by I factorial. So this is nothing but this exponential of x. So this can be replaced as exponential of this constant, which is this one. Note that this size of w and side of w is cancelled. Now after that, because both are exponential, I can take them inside same exponential, and then I can take lambda common. So what I get is exponential minus lambda size of w minus gx dx. Now we notice that w is nothing but the integration of dx over w. So I'm going to replace that. This will be integration over dx. So then I can take both common and I get 1 minus gx dx. So this will be the PGFL for the uniform PPP. Now this is for the w. Now as we take w to infinity, the complete all RD space, to cover all the complete RD space, then this will converge to the PGFL of f. The PGFL of f would be equal to exponential minus lambda integration over complete RD space 1 minus fx dx. Now we will discuss some of the functionals for point process. So first is probability generating functional, that there be a function f from Rd to R. So it takes a location and gives a real number. And let's assume this is a positive number. Then probability generating function is defined as, you go to each point and then you compute the value at that point, and then you multiply this value at every point, and then you compute the expectation of it. That is known as the probability generating function. Note that it is functional because it is a function of functions. If you change function, you will get a very different value. Now if I know the value, this value for every function, it uniquely characterizes the point process. So 2 point processes, if they have same PGFL, it means they are same in distribution. So let us see how we can compute this. For a, let's assume there is a function. The PGFL of point process phi is given as this. And if we take an example, the standard example we took, there one point take two realization. One is this one and this one. So for PGFL, if you want to compute for the first realization, what is the value of function? At here it is 1, it is also 1, so the product is 1. This means this product takes value 1 with 1 by 4 probability. Similarly here, this is 0, this is 2 and this is 8, so product is 0. So this takes value 0 with 3 by 4 probability. So expected value would be 1 by 4. Let us compute the PGFL of uniform binomial point process in one point in domain W. So the PGFL is defined in the following format, and you have to take a product over all points, compute fxi and then take expectation. there is only one point, so there will not be any product. It's just one function fxi. So let's call it fx1. So what I am interested in computing the expectation of fx1. Now this we have already computed in the past. E of fx1 is given as integration of fx lambda dx. So if I put that, that will be my PGFL. Now let us extend this to compute the PGFL of binomial point process with n points in domain W. So the PGFL is again given by this, and there are fixed n points here. So this is a product over n points for each fxi. Because this is a deterministic product, I can take this product outside the expectation, and this will become the product over n terms of E fxi. Now note that each of these terms is same. Okay, these are points are identical, distributed. So EFXI and the sum product of similar n terms would be just this term multiplied by n times. So this will be this to the power n. So what I get is expectation of fxi to the power n. And this I have already computed in the past. This is given by this way. So if I take and replace this, I will get this PGFL expression for the binomial point process. We now compute the PGFL for PPP. We first tell the result that for a PPP with density lambda x, the PGFL is given as exponential 1 minus of x lambda x dx integration over RD. So now we'll see its proof. We'll start with the uniform point process, and first we will only take points inside W. So I'm going to define a new function x gx, which is fx if x is in W, and otherwise it is 1. So all the other points which are outside this set W, their value is just 1. So if you multiply them, it will not change the product. In other words, I'm only considering the point inside W, and for outside point I'm just ignoring them. And if this W is large enough, the PGFL at G would be equal to PGFL at F, because eventually if you take W very large, you end up taking all the points. So let us compute the PGFL of G first. So to compute that, I am going to condition that W has n points. This W is finite set, so it will only take finite values, and the number of points in W is a Poisson distributed random variable. So first condition that it has n points, and once I condition that, we know that the whole point process looks like a binomial point process in W, which means each point is uniformly distributed in W. So what will be the condition PGFL conditioned on that their endpoints is going to be equal to this. So this is because they are endpoints, and for each point the expectation of gx would be expectation of gx dx 1 upon a size of W. So dx upon size of W is the probability that the point will be in x. You multiply it by gx and you integrate it over set W, and because each point is identical, the product expectation of product of n points would be equal to this to the power multiplied by n times, so this power to the power n. Now for unconditional PGFL, now I have to take this distribution of n and decondition it. So the PGFL unconditioned PGFL G would be, you take summation over all values of I, you compute probability that this n is I, and then you multiply the PGFL condition that this is n equal to I, condition on n equal to I. So probability that n equal to I is equal to this value. This is because n is a Poisson random variable with parameter lambda into W. And then this conditional PGFL is given here like this. So what I have is this, and first I notice that this is in the form of 1 upon I factorial into some constant to power I, and we can this is same as this one, that is summation over x to power I divided by I factorial. So this is nothing but this exponential of x. So this can be replaced as exponential of this constant, which is this one. Note that this size of w and side of w is cancelled. Now after that, because both are exponential, I can take them inside same exponential, and then I can take lambda common. So what I get is exponential minus lambda size of w minus gx dx. Now we notice that w is nothing but the integration of dx over w. So I'm going to replace that. This will be integration over dx. So then I can take both common and I get 1 minus gx dx. So this will be the PGFL for the uniform PPP. Now this is for the w. Now as we take w to infinity, to complete all RD space, to cover all the complete RD space, then this will converge to the PGFL of f. The PGFL of f would be equal to exponential minus lambda integration over complete RD space 1 minus fx dx. The PGFL can be used to compute void probability. Void probability of a set S is defined as the probability that there are no points of the point process in this set. Mathematically, you can write as V phi S, which is the void probability of set S for the point process phi, is equal to probability that there is no point. So number of point in S is 0. This can also be written in the following way. You go to each point and ask, are you not in S? And every point say yes, it means every point say that it is not in S, it means there is no point in S. So this is also equal to expectation of product of indicator that xi does not belongs to S. So you can see that this is in the form of PGFL. If I define a function from RD to 0, 1 such that fx is indicator that S does not belongs to S, then this is nothing but the expectation of product over all this function at xi. So this is basically just PGFL of phi for this point process. So void probability of S is the is the PGFL of the indicator function of x not being in S. So how can we compute this for Poisson point process? So note that for Poisson point process, we know the expression of PGFL. It is given as the expectation of product of fxi is equal to exponential minus integration over RD 1 minus fx lambda x dx. So I have to just put the function f here, and then I will get the PGFL for the function f, which is mentioned here, and that will be my PGFL. That will be my void probability. So if I put down the function f, so f is nothing but indicator that xi does not belongs to S. So now 1 minus indicator xi does not belongs to S is equal to indicator that xi belongs to S. Okay, so 1 minus will just negate this indicator, and what to get is indicator that x belongs to S, and then you have to integrate it over RD on lambda x dx. So you can see this integration will be whenever x is outside S, this will contribute 0, and whenever x is inside S, it will contribute 1. So this is nothing but just the integration of lambda x dx over set S. And what will you get if you integrate the density over the set S, you get the expectation measure of that set. So this is equal to expectation minus lambda S. And if this is a uniform Poisson point process, then you will just get lambda into small lambda into size of S. Because for a uniform Poisson point process, the expectation measure is just the density multiplied by the size of the set. So this is the void probability of the set S for PPP. And by this method, you can compute it for any point process whose PGFL you know. Moreover, this for Poisson, there was an easy way to do this. we know that phi s, the number of point in set S for any S, is a Poisson random variable with parameter lambda s. Okay, so this is by definition that if you take any set, number of point in that set is a Poisson random variable with parameter equal to expectation measure of that set, lambda s. So what is the probability that a Poisson random variable is 0? It is equal to exponential minus its mean. Okay, since phi s is a Poisson random variable, probability that this Poisson random variable is 0 is equal to expectation of minus mean, and the mean of this random variable is capital lambda s. So you could have directly gotten it for the PPP, but for other point process, you can use PGFL to compute the void probability. So where we can use this void probability? Void probability also help us characterize the point process. I'll talk about one particular application. Suppose you want to compute the distance of the closest point from the origin. So let us assume this is origin, and this Poisson point process is homogeneous with density lambda in the space of R square. And I would choose the closest point and I compute its distance, and I would want to, it's a random variable because the points are random. So what is the distribution of this? So I want to compute the, suppose the CCDF of this RC. So probability that RC is more than A. Okay, so this is the ball of A, and probability that RC is more than A, it will only happen if there is no point in this ball of A. If there is any point in this ball of A, then one of them will be the closest point, and that distance will be less than RC. So RC, the closest distance point, can be more than A only if there is no point in this ball of A. So what is the probability that there is no point in this A? It is given by the void probability of this ball. So that will be equal to exponential minus density into size of the ball, and the size of the ball is pi A square. So this will be exponential minus lambda pi A square. And from this CCDF, we can also compute the PDF. PDF is given by the given as minus of derivative of this CCDF. So it's a derivative of CDF or the minus derivative of CCDF. So if I differentiate it, I get this one. So this is the distribution of PDF of the closest point distance, which we also call as contact distance distribution. Okay, so this RC, the closest point distance, is known as contact distance, and this is the contact distance distribution. And you note that instead of origin, if you take any other point, distribution will be still same because this is a stationary point process. Another way to characterize a point process is using Laplace functional. It is defined the following way: for any function from Rd to R plus, the Laplace function of a point process for this function is given as, you go to each function, each point, you calculate fxi, you add over all points, take exponential and minus, and then you compute the expectation of this with respect to all realization. This will be Laplace function. And again, you note that this is a function of function. If you change this f, you get a different value. So if I am able to characterize this for every possible f, then I say that I totally characterize the Laplace functional, and Laplace function can also totally characterize the point process. It means if two point processes have same Laplace function, then that means they have the same distribution. And you can notice that it has very similar form as the PGFL, and in fact they are interchangeable. From PGFL you can compute Laplace functional, and from Laplace function you can also get PGFL. So how can we see that? You can see that this is a summation, exponential of minus summation. So I can take this summation outside the exponential to get a form of product. So this is same as saying product over all point E of minus fx. And if this is my function g, then this will be the PGFL. Okay. So if I take the PGFL of h of f, where h is this exponential function, and I apply it over function f, then the PGFL of this is equal to Laplace function. So I'll just state some result and you can prove them, because we have gone through how we can compute the PGFL for these. So Laplace function is either you can compute the same way directly, or you can just use PGFL to get this. The Laplace function of binomial point process for n points in the area W is given by this 1 upon size of W integration of e minus fx dx to the power n. And for PPP with density capital lambda, density small lambda x, the Laplace function is given as exponential minus 1 minus e to the power minus fx lambda x dx. And you can notice this is just replacing g or f on the PGFL by e to the power minus fx. Where can we use this Laplace function? Suppose let's take how we can also simplify this further. For a two-dimensional point process, I can either write in terms of Cartesian coordinates, or I can write in terms of polar coordinates. Polar coordinates is very much sometimes is useful. So for polar coordinates, I will convert xy to r theta. In that case, dx dxy will become r dr d theta. So this will become the integration from minus pi to pi, or 0 to pi, 0 to infinity, 1 minus exponential of, here the function I will define in terms of r and theta. Okay. And then density will also be defined in terms of r and theta, and this then will be r dr d theta. And if suppose the function is only distance dependent, it does not depend on angle, just the distance, though I can write it the function as fr only. And the PPP also is a rotation invariant. It means it is same in all the direction. Then the density will be only a function of r. I'll just write as lambda r, and then Laplace function can be given in the following format. The one integration with respect to theta will go away because this term is independent of theta. We just get 2 pi here. So 2 pi and then 1 minus exponential of fr lambda r d. So let us see example of this Laplace function. It is very useful in computation of Laplace transform of random variables of the following format, where you have to go to each point and then you compute a function and take the summation. So this will be, if you notice, this is a function of omega, because phi is a depends on outcome. So the whole summation depends on outcome. So this phi omega is nothing but a random variable. Sorry, f omega is nothing but a random variable. So if the random variable is defined in the following format, you can write in the summation over all points of some function, then the Laplace transform of this function, which is e to the power minus sf, can be written in terms of Laplace function. So you write f, so it will become e to the power exponential of minus s into summation of fxi. So that is in terms of Laplace functional format. So you can compute its Laplace transform. So what is one interesting example for that? I'll show you how interference can be written, shown in terms of this. So base stations are run. Let's take this example. So in this example, we assume the base stations are randomly deployed in an infinite two-dimensional space, and their locations are modeled by this Poisson point process, 5BS. So if there is a receiver at the origin, it will face interference from all these base stations, and we are interested in computing what is the sum interference at the origin, which is a random variable, because this realization are random. It's a function of sample space. So the interference which is computed at every point and the summation of it is also a random variable. So in particular, we define interference. If we go to one base station on xi, its power, its interference from this base station is known as, is computed as transmit power multiplied by xi to power minus alpha. And this is the distance to power minus alpha. This is known as path loss. More the distance, higher the path loss. And this alpha is known as path loss exponent, which depends on the environment. If it's a free space, it's taken as 2. If it's a very high scattering environment, then you take as a higher value, which is 3 or 4. And then this is the interference from one base station at xi, and you added this interference from all base stations, you get a total interference at the origin. And we are interested in computing the distribution of this. So for that, we can compute the Laplace transform of this interference, and from Laplace transform, someone can hopefully get the distribution. So if I Laplace transform e to power minus si, right, and then if you put it this, will become e to power minus summation of sp xi to the power minus alpha. So you can look at this is nothing but the Laplace functional of this function sp norm xi minus alpha. Okay, or you can take PGFL also with the modified function transformation, that will also work. So you can say that for a PPP with density lambda x, the Laplace functional is given as exponential of e to the power minus. If I have this x extra, this will just get absorbed in s of x. So this will become exponential minus 1 minus e to the power minus s f x lambda x dx. Okay, so there is a s term here. So there will also be s term here. So Laplace transform of some interference would be then computed. If I put the function value with s here, this will become spx to power minus 4. Suppose alpha is 4. And then we can compute this integration to get this exponential minus pi lambda pi sp. So now you can see that in the past, when we talk about the interference from different base station at a particular location, there were so many random variables and it was difficult to compute that. But using the Poisson-Point process, we are actually able to compute a closed form closed form value of this Laplace transform of the sum interference. From this, we can see that as we increase lambda, this Laplace transform decreases exponentially. Now, in the end, we compute the technical requirement for Laplace transform or the distribution of this as to be to exist. A 5-year uniform Poisson-Point process with density lambda, and f is a function from Rd to R plus, and it's a measurable function. Then the summation s equal to summation of fx is absolutely convergent almost surely if and only if this integration is finite. This integration is you take the function absolute value and you compute a minimum and you take the integration over the space. If this is convergent, then you get the get that this summation is also absolutely convergent, and then its Laplace transform or MGF will exist and given by this. So what does this condition means? It means that a function takes some high values at some bounded support, that is fine, because then I will take the minimum with 1, and so I will integrate 1 over that region, and that will be bounded finite. Right? But if the function takes more high values for infinite space, then this this integration will not be convergent. And also, if they take small values, but the overall integration is not finite, then also S will not exist.